Okay, our final will be Wednesday, so you have a couple days to, well, I guess finish up other classes. But 10:30 to 12:20, it's designed to take 2 hours, but most students get done hour to hour and a half. But there's some that get stuck on a problem and will take probably 3 hours if I let them. And usually it won't do any good anyway, staring at that problem going, how do you do this? But anyway, there are 20 problems on the final, so not much. I mean, about a regular size final. This last one we only had 12, but most of them have been 20 problems, so not much more than regular test. The thing is, it'll be a little bit of everything. We've had 5 units. I won't say there's exactly 4 problems from each test, but give or take 1 or 2. So a little bit of everything. And today we'll start going through what problems to expect and kind of remind yourself, especially today we'll go through the first ones and remember what we did way back at the beginning. Seems like a long time ago now. Oh, and I guess one thing I should mention, I will allow you 1 sheet of paper with notes and formulas and whatever you want to put. So,
Can you write down like the worked-out example?
sure, whatever you want to put on it.
I'm gonna write lab problem.
This is a regular standard size sheet of paper, 8.5 inches by 11 inches. Both sides is fine. So plenty of room for you. You don't need the 8.5 meters by 11 meters. And see, I did put my units on here. So that's another thing you need to remember is units. Okay. Well, as I said yesterday, the best way to study for the final is look over these old tests, and we'll just kind of go through test by test and work through some problems and remind you of what you did earlier. And test 1, we did a lot of limits. Calculating the limit, evaluate the limit, find the limit. And we've seen a few different types of setups on that. Well, and then we did look at a few other things from test 1, but half of test 1 was find the limit. So let's see, x approaching. Let's see if I can. That's, I know what I'll do. We will change this problem slightly. Whoa! The eraser got a little big there. How about x approaching 3? What do we do to evaluate this limit? Okay. What's the first thing we need to do, though?
You plug in the 3 to see.
Okay, plug in the 3. Well, plug in the 3 and what do we get?
0, 0.
Okay. So very first thing, check that. That would save a lot of work. If it's not 0 over 0, then you're pretty much done. But if it is 0 over 0, we have more work to do.
What if you get undefined? Then it's undefined.
then it's undefined, yeah. If it turns out to be like 5 over 0, then
Zero.
it's undefined and you're done.
Oh, sorry. Yeah,
So, but 0 over 0, of course I'll try to put them, most of them anyway, at 0, 0. So yeah, getting the 0 over 0, factor the top and bottom. Okay, what do they factor into?
X minus 3x plus 2 on the top. And then on the bottom would be x minus 3x plus 2.
Okay, so x minus 3, x plus 2, x minus 3, x plus 1.
Okay, yeah, yeah.
And our x minus 3's cancel out. And that's the real reason why we have a problem here with the limit as x approaches 3. Get rid of that and we're down to this smaller fraction that we can just plug in now, and we get the limit equals 5/4. So that's definitely the most straightforward limit. We'll take a look at a couple other limit problems that you have to do a little bit more algebra than just factoring. And one of those, I'll just pick one off the test. Try not. These are a little harder to make up off the top of my head, so. Something like this. Again, plug in -2 in for x, and what do we get?
0 over 0.
Okay, again, we get the 0 over 0. A little more work to figure that out, but now the form of this one is a complex fraction where we have fractions in the numerator and or the denominator. So what do we need to do to simplify this?
Combine them. The ones on top.
Okay, we could combine the fractions on top, or we could do something very similar to get rid of the fractions on the top. Probably the easier way, or the way that has the least amount of work to it, multiply the top and the bottom by the least common denominator. Okay, which would be, yeah. Now, what we really want to do here, multiply through the top especially, and that'll simplify. We don't really want to multiply out the bottom. Most of these limits we're trying to keep them in factored form so things will simplify. So don't multiply out the bottom, but multiplying out the top, we get what? Multiply this by x minus 3's would cancel, and we get the 1 times 5 would be left over. And then this times the 1/5. Well, 5 times 1/5 is 1. And we get the x minus 3 left. Now, this is one place where little mistakes can occur. In this case, it's not going to be because we have a plus. But if that was a minus, make sure you're putting parentheses around this, because it's minus that entire quantity if it was the subtraction.
If it's plus, doesn't matter.
Plus doesn't matter, but the minus definitely does matter. Now a little bit of simplifying up top, combining like terms. We end up with what in the numerator?
5 times 5. Oh, you end up with 1 over x plus 2.
And then 1
How
Oh,
about
1 over 5x plus 10.
okay, the 5 plus x minus 3, we end up with x plus 2. And then you see y in the denominator. We don't want to multiply all that out because now we can do what? X plus 2 divided by x plus 2. Now remember, we still have a 1 in the numerator. It's not 0, but a 1 in the numerator.
But how do you get the x plus 2 on the top?
5 plus x minus 3. 5 minus 3 would be 2, and that's, we're adding or possibly subtracting. So in those cases, you got to combine your like terms. So now, well, we can finally plug in our negative 2 in for x, and we don't get 0 over 0. In this case, we get 1 over 5 times negative 5, or limit of negative 1 over 25. Okay? Questions there? Okay. So, okay, after a little technical difficulty there, we're back. Limit, this time involving the square roots. Once again, plug in 1 for the x, and what do we get? Okay, 0 over 0, so we've got some more work to do. And with the square roots in the numerator, what do we need to do to simplify that one? Okay, right, multiply by the conjugate. Square root of x plus 2 plus square root of 3. And once again, we're not going to want to multiply the denominator out, but definitely multiply the numerator out. Get x plus 2, then the square root times the square root, and then minus the same square roots. Those cancel out. That's why we multiply by the conjugate, so the middle term, if you will, cancels out. And then the last we'll get negative 3. And then as we combine like terms up top, what do we get? So what can we do from there? Okay, again, the x minus 1s we can cancel. And we're now ready to evaluate the limit 1 over this expression, and plug in the 1. We'll get a square root of 3 plus another square root of 3 in the denominator, or 1 over 2 square root of 3. And that form is fine to leave it in. Okay. Questions? Now, in a lot of our problems, test 1, I guess we're given the graph of something and figure out some different things. We'll just kind of choose a few things here to work with. So if we look at this, and let's see. I guess put in negative 2. What would f of negative 2 equal? Okay, it's going to be 0. Well, we've got the graph would be on that particular point. What about f of negative 1? That's going to be 4. Now, what's happening at negative 1 that can cause us some problems? Okay, it's a jump discontinuity. We have one part from the left, it ends at this point and then jumps up to this point. So why is it not f of negative 1 equals 2?
Just a whole.
Okay, we have the open circle, the hole in the graph at that point. And let's see. What can we say about this? The limit as x approaches negative 1.
No, it's a jump
Two.
discontinuity.
This is negative
There's no limit because it's only from. It's not
Okay, does not exist. Now, we can break this down a little farther and get answers and show why it doesn't exist. If we look at x approaching negative 1 from the left, what would that equal?
It's about two.
Okay, that's the 2. Okay. From the left, it's approaching the value of 2. Okay. But then from the right, the value would be what? Okay, and that again goes back up here. Whether that's a solid dot or an open circle, that doesn't matter. That's still going to equal 4. Okay. But because these are not the same value, then the limit as x approaches negative 1 does not exist. Okay. Small detail there. Well, where is a limit that would exist, but the function is not continuous at that x value? Okay.
Is that 2 or 1?
2.
Oh,
Here's 1. So, now at x equals 2, we can say the limit as x approaches 2 equals 1. Both sides are approaching the value of 1, but, well, for a couple reasons, f of 2 is undefined. And because of that, we have discontinuity at 1. Okay, even though the limit exists, it's discontinuous because f of 2 is undefined. Well, what if we were to define the function at x equal 2? Let's say we change our function a little bit and put a solid dot down there. Do we have continuity at that point? Okay, in this case, I guess we should say second scenario, f of 2 exists and would equal, let's see, negative 3, but we still have discontinuity at x equals 2 because of what? The limit value does not equal the function value. Okay. And in that case, we would call this what type of discontinuity?
Removable discontinuity
Removable. Okay.
when it's undefined, right?
No, it's removable when the limit exists, but the limit value doesn't equal the function value.
Right?
Whether it's undefined or something different than the actual limit. Okay, it's when the limit exists, but it does not equal the function value. Whether the function value is undefined or somewhere else.
Because of, yeah.
Yep. Okay. And then lastly, what's what can we say about x equal 3? Do we have continuity there?
At f of x equals 3? Yeah. So you have a continuity.
Kind of that situation. Do we have continuity at that point?
Yeah.
Okay, yes, we do. We're down here at -5. From the left and from the right, we're approaching the same value, so the limit would exist.
Because it gets closer.
Okay.
It's just
And it's a solid dot, or even if I didn't put the solid dot, if we drew it this way,
it's undefined.
okay, then the function value is defined, and that function value is the same as the limit. Okay, so the limit exists, function value exists, and they're equal, so it's continuous at that point. But one step beyond that, we talked about what? Leo, I think you said,
There's a, because of the cusp,
yeah, because of the cusp.
the derivative, the first derivative, one of the critical points, it's undefined.
Okay, the function is not differentiable at that point because it's a cusp. It's not a smooth curve. And theoretically, we could show the derivative coming from one side is not the same as the derivative coming from the other side. But continuity, it is continuous here, but because of the cusp, it's not differentiable at that point. Okay. So a lot of stuff that we covered there. Now, we may run into some functions in equation form as well and ask, is it continuous or discontinuous? Yes, how did I ask that? Find the x values at which f is not continuous. So we'll take a look at some of those as well. Now, a lot of times we looked at piecewise defined functions for continuity. And really, as we look at the function, the equation, this is a linear equation. This is a linear equation. So the only problem point would be where?
Or x equals 1.
At x equals 1. Where it switches from one part to another. Now, as we saw with the previous problem, the cusp, that would be a piecewise defined function if we were writing that out, but we saw continuity there. So it is possible to have continuity at x equals 1, but it may not. It may be one of those jump discontinuities. So we can't just look at the formula and see. The idea, well, first of all, this says f of 1 equals -1. So the function value is defined. Okay. Usually with a piecewise defined function, it's the limit. We've got to see whether the limit exists. And in this case, well, the limit as x approaches 1, I guess, from the left, when x is less than 1, we're essentially looking at this limit problem. And here we can just go ahead and plug in 1 for the x value. What do we get?
2 plus 3.
What?
2 minus 3.
Okay, 2 minus 3, which is then -1. Now, careful, this notation means from the left, not -1, but +1 from the left. Okay. Well, what about x approaching 1 from the right? Okay, so -1 again. That shows us that the limit as x approaches 1, we don't have to break it up anymore from the left or from the right. Since those are the same values, it's going to equal that number. And then we go back to the very beginning. F of 1 equals -1. So that tells us what? Okay, this function is continuous at x equals 1, which then we can say it's continuous for all real numbers. I guess we're looking at -infinity to positive infinity. And the question on the test is, where, if any, is it discontinuous? So we could answer that. No place is it discontinuous. It's continuous everywhere. Now, had this been some different value than -1, well, the limit still would have existed. The function was defined, but this part would not have been true, so there would have been discontinuity. Yep.
What if it says like x is equal 1, but it says 0?
If that would have been
If that
0,
was 0, it means
then
it's undefined?
no, it would mean f of 1 equals 0.
Oh, okay. So
If that had been 0, then we would have discontinuity. The limit was -1, but f of 1 equaled 0, so we'd have a
there's like a
hole in
circle
the
at
graph.
that point,
Yep.
So it's a rule of discontinuity?
Exactly.
So how do you know when it's undefined?
Well, this
It would
right
tell you-
here defines it. Anytime we have the equals included in the function, whether it's by itself or perhaps had this been x is greater than or equal to 1, then we're defining the function for x equals 1. If the equals is included, then f of 1 would be defined.
What if it's like it doesn't include it?
Okay, if it would just be
Yeah, that
the top 2 lines of this, then x equals 1 is not defined, or f of 1 is undefined. That would be that situation. Okay? So lots of different possible problems like that. All right. Now, after we talked about the limits and continuity and then kind of touched on the differentiability as well, we started looking at the, well, we didn't call it the derivative at the time just yet, but the velocity, instantaneous velocity, slope of the tangent line, okay. I guess we'd talk velocity pretty much there. Didn't get into the acceleration just yet, but kind of brings back some of the things we talked about just this last unit, except instead of starting at acceleration and working our way back up, we started at the position and worked our way down. First derivative of the position function is the velocity and so on. Now, in test 1, we hadn't seen the shortcut derivative rules, but now we have. So on the final, if there's anything, find the instantaneous velocity, find the slope of the tangent line. You can do that using the derivative rules, the shortcuts. However, there is one more problem here on test 1 that does say use the definition of the derivative. Derivative. Okay. To calculate the derivative of some function. There will be something like this on the final. So, let's see, we had f of x equals x squared plus 4x minus 10. Well, to find the derivative using the definition, you remember the definition?
Yeah.
Limit
As x approaches 0.
as delta x approaches 0. Okay. Of
X plus delta
F
x.
x plus delta x minus f of x divided by delta x.
okay. Very good.
Wouldn't it be like x plus delta x minus x, but the two x cancel out? So you
Correct. Correct. And again, this part of it without the limit, that's really just the slope of a line through 2 points, x and x plus delta x. So yeah, like you were saying, the difference in those x values, x plus delta x minus x, the x's cancel in the denominator. We just have this. So again, kind of why we can use this as well for slope of the tangent line. Okay, and then just lots and lots of algebra and a tiny bit of calculus at the very end. This is usually the tricky part. Plug in x plus delta x, the binomial factor, into our function. And then the other spot where we find little mistakes every once in a while, subtract the quantity of f of x. So yeah, we'll multiply that negative through as we simplify. But there's the setup, and then here we've got tons of algebra to do. X plus delta x quantity squared. Remember, that's not just x squared plus delta x squared, but we have a 2x times delta x in the middle. And then minus x squared minus 4x plus 10. Make sure you get that negative distributed. And then finally, combining like terms on top, x squared minus x squared, 4x minus 4x, negative 10 plus 10. And we see we're left with only 3 terms in the numerator. What do all 3 of those terms have?
Delta x.
Right. And if you're not able to cancel everything out except the delta x terms, then you made a little mistake, and might be a good time to go back and try to find that. Usually right here, forget to multiply the negative through. Or sometimes you forget about the binomial square. So with these 3 terms left, all of them having the delta x in it, we'll go ahead and jump to the step we can factor out the delta x. Now it would leave us with 2x plus another delta x, since we had delta x squared there, and then the plus 4. And ultimately, the reason we want to do that, we've got that delta x on the denominator that will now cancel with the delta x in the numerator. And finally, we're ready to take the limit, evaluate delta x approaching 0, so we'd have 2x plus, well, the delta x approaching 0 would go to 0 plus 4. So the derivative using the definition would be 2x plus 4. Now, I would hope that you know that already, but always a good thing to go back and check and make sure from your shortcuts you get the same thing. If not, well, try to find your mistake in there. But question?
Why do we do it on the test if we learn the shortcut? Is it just to show it?
The reason we do that is to kind of see if you really understand the meaning behind the derivative, not just learning operations. Yeah. So, okay. Now, in the last part, again, we've talked about some of the applications of the derivative, velocity and position, slope of the tangent line. We've seen that in later tests as well, so we'll wait on those until go through those on some other tests, since we won't need to go through the definition on those. You can use your shortcut. Okay. So test 1, some things that we haven't done in a while, and that's why I spent so much time just on that part. Now, test 2, we did a lot of work with the shortcuts, the derivative rules, and we've done that fairly recently as well. Even though we've done integration the last couple units, we've had to do some derivatives when we do substitution. But definitely make sure you know how to find the derivative of any form of these functions. And test 2 was almost all find the derivative of. You got your power rule, which once in a while gets a little confusing, especially now that we integrate. We got to remember which direction we're going. But 1 over x squared or something like that, make sure you get the x to the -2 and treat that the right way. Product rule, quotient rule, chain rule. Again, those we've done quite a bit of lately. Then some of our special functions, the derivatives of your trig functions. Derivative of sine x is what? Cosine x. Antiderivative of sine x is negative cosine x. So again, watch which direction you're going. And trig functions, some of those we haven't worked with for a while, and you do have that sheet of paper, you may want to just jot those down just in case. And then going backwards is your antiderivatives. So probably the most missed problem on test 4 was working with those trig functions, the cosecants and all those really common, well, maybe not so common, but something you should know. But okay, trig functions, derivatives, the exponential, and I'll limit that to the e to a power, not your 2 to a power or 5 to a power. And then the log, and again, I'll limit that to the natural log, not log base 2 or log base 10, but natural log. But along with the natural log, Sometimes it's much easier if you use your log properties to rewrite the function before you take the derivative. So keep that in mind. Some of these get real ugly if you just go directly to the derivative. Let's see. So lots and lots of derivative problems on test 2. Then some of the details, some of the other details, evaluated derivative. So first you got to find the derivative of the function, then simply plug in x equals 4 into the derivative function. We've done that quite a bit now for a while, and especially one of the applications, find the slope of the tangent line at a certain point, find your derivative, plug in the x value to find the slope, and then find the equation, use your line linear equation formulas to find that. Another thing that we kind of introduced in test 2, we haven't done much with it lately. Implicit differentiation. Given something like this, find dy by dx. So just be careful with that. And we went both dy by dx and dx by dy. But on the final, we'll just only the dy by dx. Or perhaps it'll be find the equation of the tangent line at some point. But again, it's finding dy by dx. I'll run through that real quick. Derivative of this, well, with respect to x, is just 3x squared. But this next part, we would have to do what? Okay, product rule. So first times the derivative of the second, well, derivative of y with respect to x is that dy by dx. So remember that. And then plus y times the derivative of 2x. Well, that's just 2. So that term will have 2y. And then finally the y cubed. Well, it will still be the 3y squared, but then times dy by dx. And derivative of 1 is 0. Then from there, solve for dy by dx, or if it's a find the equation of the tangent line, you could plug in the point in for x and y, and then solve for dy by dx. Algebraically, that's a lot easier to work with the numbers for x and y. But if it's find dy by dx, then you just have to plug through that and be careful. So, and then once again, the last few problems were the velocity, and this time we threw in the acceleration, second derivative. So we've done a lot of that lately as well. But that's pretty much test 2. Look over test 2, and if you have any specific questions, we'll cover those tomorrow. Kind of running out of time. But tomorrow we'll look at tests 3, 4, and 5. Any examples on those as well.